Okay, this is a synthesis problem. We have to synthesize the following molecules from hydrocarbons containing 3 carbons or less. So we have a bromide. Well, one thought is to immediately start thinking about adding that bromide via addition across an alkene. Now, if we add HBr, and just draw in that, saying the H and the Br came from HBr, this is not exactly a very good synthesis because, first of all, there is no stereo control over adding the H and the Br. If you were to treat this molecule with HBr, you would end up, well, protonating, and that hydrogen can come from one face or the other face, and then the bromide can add from one face or the other face, and as a result, you end up with a mixture of diastereomers. Where you have the H and the Br adding on the same face and the H and the Br adding on opposite faces. Moreover, this is a Markovnikov addition, meaning you're going to protonate the less substituted side. Well, each of those carbons are equally substituted. So you would also end up protonating on this side to form this carbocation. Then that bromide can add to that. And so you'd end up with this set of constitutional isomers. So you'll end up with 6 products total. So we can't use that directly. But another way of adding a another way of adding a bromine to a molecule is by doing so by an SN2 reaction, specifically using PBr3, which transforms OHs into bromides by an SN2. And this is particularly useful because it doesn't really do that many side reactions. So, and then this OH then would have to be a wedge to show the inversion. Now, going backwards, again, now we have to add H and an OH across. Now, a very good reaction to add H and an OH across is hydroboration. Because what hydroboration does is it adds the H and OH syn to each other. All your other reactions of hydration, such as catalytic acid and water, or oxymercuration, followed by demercuration, these give a mixture of syn and anti. So a way of cutting down on the number of diastereomers you make is simply by using hydroboration. And if we look right here, the H and the OH are both wedges as they are drawn. And so they are already in that nice syn conformation. So we draw the lines exactly as they are. Add in the double bond V. Okay. But the problem with this synthesis is, again, hydroboration essentially, we take a look at this, adds the OH on the less substituted side. Again, we have the problem of it being equally substituted, so if you just use hydroboration on this, you'd end up with the product that you want. Plus the product that you don't want. Now, one way around this is, instead of adding an H and an OH, you can add an OH and a hydrogen that's actually a deuterium. And if you do that, so make that be D3, what you then need to do is take a look at this molecule. Right now the OH and the D are anti to each other, so we need to redraw this molecule so the OH and the D are syn to each other, like that. So if we do so, means that propyl group's going to be a dash. This propyl group here is going to be a dash. We can double check. That's an S chiral center. That's an R chiral center. S, R, it matches up. Here we have them in the syn position. We notice that both those propyl groups are both dashes. That suggests that the alkene would be a cis alkene because they're both dashes. If one was a dash, one was a wedge, then it would be a trans alkene. Now if we look, this molecule is symmetrical. So it doesn't matter which side gets the D, which side gets the OH, you get the same product. You'll just get the enantiomer. Now with a cis alkene, we make cis alkenes by H2 and Lindlar's. And I'm going to start out by drawing the alkyne that that's react with in each side of the alkyne. That's a propyl group attached. And since the two sides are the same, we can do a shortcut of taking a doubly deprotonated acetylene and reacting that with propyl bromide. The way we make doubly deprotonated acetylenes is we use an excess amount of sodium amide And then this is a hydrocarbon. We don't have to make this. This propyl bromide is not a hydrocarbon, so we do need to make that. The bromine, we can make that from an alkene. And we want the bromine to be on the less substituted side. So we can use HBr and peroxides for that. Or if you wanted to, you can use PBr3 again and this alcohol. And then the alcohol can come from the alkene using hydroboration. Like so.